Welcome to the next lecture. We will continue our discussion on the decoding of linear block codes. So let me first describe what we want to do. See, we have transmitted. Okay, let me tell end-to-end story. Okay, so that whatever we have covered till now, it gets reflected. So there may be an analog signal. Okay, there may be an analog signal. Suppose m of t. You first do a sampling, then you do quantization, then you do PCM. After that you use it to do line coding and modulation. But here after PCM, immediately we have this channel coding, right? It is at this point that we are adding these extra bits so as we can recover the errors. And now after channel coding there will be modulation. So if your suppose message bits were this and your channel code was 010, so this should be 0101. Suppose this is the message channel code. So we will not, so earlier we used it to modulate directly. 0 we used it to represent by minus root E level, 1 by root E level, and then use BPSK. Now we will modulate this channel code and transmit it over the channel. And noise may change one of the bits, that is the error, and we want to correct the error. Okay, so after modulator, so there will be a channel, and then at the receiver the first thing we will have to do is demodulate. And after demodulation, what will you get? You will get bits, right? But that may have error, so you will use channel decoding. After channel decoding, now you will use the digital to analog converter if you want to convert it back into the message. Okay, so this is the overall picture. So we started with sampling, and then we are here. We are now here channel coding, modulation we have done. Now we have transmitted a code word. Suppose C over a channel, and we are here taking binary channel, binary symmetric channel. That is, see, it depends upon values, which point you are considering. So we are considering this as the input point, and this whole modulator channel and demodulator, this now becomes our channel. So when we take this as the input point and this as the output point, then the waveforms don't enter into the picture. We are dealing with binary numbers. Okay. Anyways, so we have transmitted this. Now at receiver, we will receive R, okay, which is the received vector. Now their received vector is basically, it is a version of C. So there definitely will be some errors. Okay, and our job is to, from R we have to deduce what code was transmitted, okay, and indirectly what message was transmitted. So definitely R is an n length vector, so R can take 2 to the power n possible values, right? It can take any of these values, 2 to the power n possible values. But for us, there are only 2 to the power k codes, with meaningful codes, right? Because we had 2 to the power k messages, and each message is assigned a code word, so there are 2 to the power k messages and hence codes. So what is the task of receiver or channel decoder? Here receiver being a channel decoder. Okay, the task of receiver is to partition this 2 to the power n possible received vectors into 2 to the power k disjoint subsets. Okay, suppose d1, d2 and d2 to the power k subsets, such that the ith subset di corresponds to ith code ci for I less than equal to 1 less than equal to this 2k. So what is the task? See, suppose this is the R and there are several possible R's depending upon the length. Let's take example that k is equal to 4 and n is equal to 7. So you have 2 to the power 4, which is 64 codes, but at receiver you have 2 to the power 7. So 128 2 to the power 7, 128 possible values of received vector are there. Now what is 128 divided by 64? So it is 2. Trivial mistake. 2 to the power 4 is 16, sorry. So it is 16 codes, and the possible values of received vector are 2 to the power 7. So what is 128 by 16? So this is 8. Okay, so we will basically do one thing. So we will have 16 different sets. Okay, and each set will contain 8 different binary sequences, right? So here will be this d1, here will be d2, and here will be d16. Okay, and in each of this there will be 8 different possible codes. These will necessarily not be codes. They will be any 7-bit binary sequences. One of them will be code, definitely. Now you received a vector R. You will see to which set it belongs to. Okay, suppose R belongs to D2, then you will declare that the code which was transmitted is actually C2. Okay, so to make it more clear how to do this, actually we will construct this table that will make the picture more clear. See, first of all, you will place all the possible code words in one row. First one you will write all 0 code word. Okay, and then next code word C2, C3, Ci, and C2 to the power k, because there are 2 to the power k possible code words. Okay, then here you will place the possible errors. Okay, so hold on with the general discussion, it will become very clear. I will take example after this. So these are the possible errors. Now what you do next is go on adding this error to the code word. So here is C2 plus E2, then there is the error E3, C2 plus E3, then there is error EJ, C2 plus EJ, then there is error pattern e to the power n minus k, so C2 plus error. Similarly, for next code word, add the error to add each of these error patterns to the code word. Okay, so what is the set? Now it will be very clear now. So these are the possible sets. Okay, so C2 and C2 added with all the possible error patterns, this forms D1. Similarly, C3 and all the possible error patterns, this forms D2. Similarly, Ci and all the possible error patterns, this forms Di, and similarly this. Now, if R, you have to check now. When you received vector, you will see to which set it belongs to, and declare that. Suppose if R is equal to C3, if you can find R is equal to C3 plus E3. Okay, so it means that E3 error pattern was responsible. Correct. Now then, depending upon how this error pattern is, receiver can easily detect at which bit there is an error and correct the error also. So as I told that, you hold on, because it will be more clear how to do it when I will take the example. I will just write here general steps, then we will see the example. So the general steps for decoding of linear block code. First of all, for received vector, R, find syndrome. What is syndrome? S is equal to R H transpose. Okay, H will be given to you. Then the second step is, okay, now some terminologies I have already told you, but let me tell again. See this column wherein you have a particular error pattern E2, and then you get other error patterns which have the same syndrome by adding code word C2, C3 to the same error pattern. I already told you in the previous lecture that if you have any error pattern and its syndrome is suppose EH transpose, sorry, if you add any code word to the error pattern, its syndrome will remain same, because it becomes EH transpose plus CH transpose. CH transpose is 0, so it becomes EH transpose. So here are the error patterns for which all of them. So first is E2, then you add code word to this, then you add C2 to this. So this is called coset. Okay, coset of the code. This is one coset, this is other coset, and the first basic error pattern, okay, this is called coset leader. Coset leader is chosen such that its Hamming weight is minimum of all error patterns. This is the rule. Hamming weight is minimum. I will tell you later on why it is so. Coset leader is chosen such that its Hamming weight is minimum. Okay, I again repeat, things will be more clear when I will take the example. Now the second step is within the coset characterization. Let me write it. So within the coset characterization by syndrome, identify the coset leader. Okay, coset leader will be the basic error pattern. We will see it later on what it means with the example. Third is that compute the code vector. See, you know that R is now C plus error pattern, so C is R plus error pattern. Simple. Just add now error pattern to R. This will be the decoded version of the received vector. So this is the decoding process. Okay, now let's take example. Example we will take from again Hamming code. Okay, which I told you in the previous lecture. First of all, you should be very comfortable with converting generator matrix into parity. See, if G is given to you 1 1 0 0 1 1 1 1 1 1 0 1, okay, then 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. This is the generator matrix for this particular code, right? Now what will be parity check matrix? That is I of n minus k p transpose. See here, n is equal to 7, k is equal to 4, n minus k is equal to 3. So you will first have a 3 cross 3 identity matrix part. Then you will take a transpose of this p here, right? P transpose. So you will get 1 0 1 1 1 1 1 0 0 1 1 1, right? So this is your parity check matrix. Okay, and you will observe that it is an example given in the book. Also you can see, if you see, except all zero code word is obvious, its Hamming weight is 0. You will see any other, suppose the one of the code word says 0001 is a message, its code word is 1010001. It has Hamming weight 3. Similarly, there is a message 4 times 1, its code word is this, its Hamming weight is 7. There is some code whose Hamming weight is 4. There is some code whose Hamming weight is I think only 3 4. The minimum Hamming weight in this code is 3, d minimum. So how many bits it can correct? You know that. So let me write that. You had done last time. D minimum is 2t plus 1. So t is d minimum minus 1 divided by 2, which is 3 minus 1 by 2, which is 1. So this Hamming code has capability of correcting only 1 bit error. Okay. Now we will do one thing. We will assume that, suppose you transmitted a message whose code word is 1110010. So it means message was 0010, which is encoded into 1110010, and it is transmitted over the channel. What receiver receives is 110010. Okay, now you know right now that there is an error definitely, and you know also error is at this position, but receiver just knows this much and knows the code structure. So what will be the first step receiver has to do? Compute syndrome. Okay, and syndrome will be computed with the help of parity check matrix, which we have already shown you. So here is the parity check matrix. So syndrome is computed by taking this R. So this is your R. Okay, this is your R, and this was the code word. So R H transpose, which will be equal to 110010. H transpose will be 100 010 001 110 011 111 101. Okay, this is the H transpose. And now you, after compute very simple algebra, you will get 001. So this is the syndrome. Okay, now see what actually how will we now form that coset. We don't have to do that much for this case. It will be very simple. Actually, what we got is t is equal to 1. This code has 1 bit error correcting capability, and we are assuming that only 1 bit errors occur. For 1 bit errors, what are the possible error patterns? They are very simple to tell. So first of all, if there is no error, definitely this is the error pattern, obviously, right? Its syndrome is also obvious, 000. So this is the syndrome, and this is the error pattern. Okay, now there is a possibility that first bit is an error, so this will be the error pattern. It means when this error pattern gets added to code word, first bit comes an error, and its syndrome will be computed separately. So you can always use syndrome can be computed E H transpose, right? Very simple. Then The other possibility is this second bit is an error, third bit is an error, fourth bit is an error, fifth bit is an error, sixth bit is an error, or seventh bit is an error. These are the only possible error patterns, basic error patterns, and we compute its syndrome accordingly. So 0 1 0 1 0, then 0 0 1. So this is this, then after that 1 1 0, then 0 1 1, then 1 1 1, and 1 0 1. So far so good. Now what does decoding mean? Decoding means what is the syndrome you got for the received vector 0 0 1. So you check here which error pattern has syndrome 0 0 1. This one, right? Hence this error pattern has occurred. Okay, in fact, if you see what that table means, so this is the code word, right? So if you add this code word, if you add to this code word the error pattern C plus E, right? So that is actually R. Now what is the C then, right? So R plus E, simple. So our R is 1 1 1 0 0 0 1 0, and E is the error pattern 0 0 1 0 0 0 0. Add them up, you get 1 1 1 0 0 1 0. So you got back the code word. So we have detected the error as well as we have corrected the error for this particular case. Okay, very simple. So this much for linear block codes. Now we will see one more way to represent a special class of linear block codes. They are called cyclic codes, and they are actually the ones which are used practically. And every cyclic code is a linear code, but every linear code may not be a cyclic code. Okay, so basically I will tell you briefly here what it means, then I will upload one more video. Suppose you have a code word C0 C1 up to Cn minus 1. Till now we have learned one thing, that if you C1 is a code word and C2 is a code word, then their linear sum is also a code word, right? But what about cyclic operation? So if I cyclic operation means if I shift this cyclically, I write Cn minus 1 C0 Cn minus 2, then I shift again cyclically, I get Cn minus 2 Cn minus 1 C0 Cn minus 3. I shift again cyclically, I get Cn minus 3 Cn minus 2 Cn minus 4. Question is, are all these cyclically shifted versions of the original code also code words? If they are also code words, then that code is called cyclic code. Okay, and the property of cyclic codes are best demonstrated by using a concept of polynomials, code polynomials, and that makes it analysis very easy, and we easily get the hardware realization also, that we will see in the next lesson.